Okay, so it's really a pleasure to have Jean-Marc Delort from Paris 13, and he will speak about inflation. Hot topic.
Yeah, so thank you for the invitation to speak here. So, yes, I shall speak about norm inflation for solutions of semi-linear, one-dimensional Klein-Gordon equations. So, first of all, let me explain what is the motivation of the problem. So, let me consider a solution of a semi-linear Klein-Gordon equation, dt squared minus Laplacian plus 1 u equals a nonlinearity n, depending on u, dtu, and varying xu. The nonlinearity vanishing at least at order 2 at the origin. And take initial conditions, ut equals 0 equals epsilon u 0, and dtu ut equals 0 equals epsilon u, where u0 and u1 are smooth and compactly supported functions on D, and the epsilon is positive and so. So it is well known that for this problem, if the space dimension D is lower or equal to 2, for small epsilon, the solutions are global. Moreover, in one space dimension, it is known also that this result, similar result, does not hold true, because there are examples of nonlinearities and of initial data, so that the corresponding solutions blow up in infinite time, even for small initial data. So such examples are constructed by Jordanov and by Kiel and Tau. So this brings to the following question in one space dimension, namely, can we find in one space dimension some optimal condition, call it C, on the nonlinearity, such that in the framework of small initial data, this condition C will be equivalent to the fact that global existence holds true for small data, and in addition, solutions satisfy the usual dispersive estimate, namely u at time t near infinity should decay like t to the minus 1/2 when t goes to plus infinity, which is dispersive estimate, which is well known for solutions of the linear Klein-Gordon equation, and which hold as well for solutions of which should hold for solutions when this condition is satisfied. So, more than 20 years ago, I actually proposed such a condition C, and I proved half of these equivalents. So let me explain what is this definition of this condition that I will call a null condition. So to do so, I will limit myself to the case of cubic nonlinearities. So from now on, I consider nonlinearity n of u dtu dxu, which is given by some homogeneous cubic polynomial p of u dtu dxu. And now I shall introduce a condition that should be satisfied by this polynomial. To explain it, I decompose P, which is a polynomial on T, Z1, Z2, as a sum of components Pk of T, Z1, Z2, where Pk will be assumed to be homogeneous of order k in Z1, Z2, and so homogeneous of degree 3 minus k in T. And now, from these pKs, I will introduce some function. I compute this polynomial pk at t equals 1, z1 equals omega 0 of y, z2 equals omega 1 of, where omega 0 of y is 1 over square root of y minus y squared, and omega 1 of y is minus y over square root of 1 minus y squared. So these quantities are actually pretty natural, because if you remember that a solution of a linear Klein-Gordon equation has asymptotically oscillatory behaviors with components oscillating like e to the I square root of t squared minus x squared and e to the minus I square root of t squared minus x squared, this omega 0 of y is just actually dt of this phase square root of t squared minus x squared when you set y to x over t. And omega y 1 of y is the dx derivative. And so we plug actually the derivatives of the phase of oscillation of linear solutions inside these pKs to form a new function, small pk, which is a function of y in the interval -1, 1. And now I shall say that P satisfies the null condition if and only if some function phi of y, which is defined as P1 plus 3P3 with the preceding notation, vanishes identically. So this will be the condition that I called C on the top of the screen. And so the question we ask is the fact that this condition is satisfied necessary and sufficient to ensure that we have, for small initial data, smooth compactly supported, say, a global existence, and in addition, dispersive decay of the solutions. So, as I said, more than 20 years ago, I proved 1/2 of the implication. Namely, I showed that if this null condition holds, then for small enough initial data, the solutions are global, and they decay like t to the -1/2 when time goes to infinity.
One question.
Yeah.
You haven't yet used the condition, right? That the nonlinearity should be vanishing for order greater than 2 in the null condition.
No, so that's a remark that I shall make now. So in the preceding slide, I assumed that the nonlinearity was cubic, just cubic. But actually, this is just for simplification, because when I proved this theorem, I showed that it holds true not just for semilinear equations, but also for quasi-linear ones. And it holds true for nonlinearities containing quadratic and cubic terms. And I don't speak of higher nonlinearities because they are negligible for this problem. Of course, when you have quadratic and cubic terms, you have to adapt the definition of the null condition, and the expression is more complicated, but the result holds true as well in this case. And let me mention also that it is not necessary to assume that the data are smooth and compactly supported. It is enough to assume that they are smooth enough, say in hs plus 1 times hs for some login of s, and that they have some decay at infinity, like xu0 in h1, xu1 in 2. So this has been proved by pasting. So the goal of this talk is to discuss the converse implication in the equivalence which was stated on the preceding screen. Namely, we want to know if this condition, this null condition, which is by this theorem sufficient, is also necessary. And I will state now the main result, which gives such a converse implication. So before stating the theorem, I need to introduce some notation. So let me take, first of all, some functions f0, g0 in S1. So these functions will be the initial conditions for our problem. And now, from these functions, let me define a new function of y, capital gamma. So it's not necessary to remember the explicit expression which is written on the screen. Let us just say that this function gamma of y is defined in terms of the initial data, f0, g0, through their Fourier transforms computed at the point omega 1 of y that I had defined earlier. So we just have to know, to remember that gamma of y is a function which is smooth on the interval -1, 1, which vanishes at infinite order at the extremity of the interval. And now we define from this gamma of y a time t star. By the equality, 1 over t star equals the supremum of gamma of y, phi of y. So gamma of y is a function depending on the initial data f0, g0. Phi of y is a function that I introduced before. It depends only on the nonlinearity. And we are taking the supremum of this product gamma phi. So remember that if phi is that if null condition is satisfied, phi is identically 0, so that in that case we get that t star is plus infinity. And actually, this is in accordance with the fact that when the null condition holds, we know that there is global existence. So
how can you see that immediately? Like if the null condition satisfied, then t star is 0. Why is that?
No, it's, this is not an evident statement. This is the theorem that I mentioned on the preceding slide. When phi is equal to 0, so this equality gives you t star equals plus infinity.
But of course, what again? Phi?
Phi is a function defined from the nonlinearity. It was p1 plus 3 p3. The expression does not matter much. It's an expression defined which is defined from the nonlinearity.
T star is not the maximal time existence.
So actually, it will be after rescaling.
It's not trivial formula.
No, of course. This is some geometric formula. Say. Now the question is, what is this T star? So we know that when the right-hand side is identically 0, which corresponds to T star equals plus infinity, we have global existence.
Is it on the V characteristics, the condition, or?
No, not really.
So this f0 and the g0 are any functions. So gamma y is positive. So
gamma of y is positive, but then of course you will you have to choose your f0 at g0 at such that if you want t star to be smaller than infinity, such that the supremum is strictly positive, and so that it is it satisfies some assumptions that we mentioned later on.
So if it's like if phi is less or equal than 0, then your t star is infinity.
Yeah, but actually here I'm looking at what happens in the future.
Okay.
And one could look also at what happened in the past.
Mm-hmm.
So if you want, if this quantity were negative, I would have looked at say the lower bound, and it will give me blowing up in the past.
Yeah.
But I'm always looking at the future.
Okay.
So to answer also one of the questions, if T star is more than infinity, we know something already. We know that if we take any constant smaller than T star, and if we solve the problem with the initial conditions epsilon f0 and epsilon g0 for epsilon small, then the solution exists over the interval 0 e to the a over epsilon squared. And it satisfies on that interval the time decay, the dispersive time decay in t to the -1. And so the question is, what happens if a goes to T star? In other words, does the solution blow up, or does it have some bad behavior? So in the future, I shall call e to the T star of epsilon square the blowing up time, even if this is a purely hypothetical name. And our goal will be to prove that this property no longer holds if instead of staying below e to the a over epsilon square, we take t to be a larger time that we call capital T of epsilon, closer to this blowing up time. So,
excuse me. So what is the explanation of P1 plus 3 P3? What is that?
well, the explanation you cannot guess it like that, of course. A way of finding this quantity is to take the asymptotics of linear solutions, say, to use them to design some ansatz. You plug the ansatz in the equation, you get some ODEs, and you see that this ODE has global or blowing up solutions, depending on the fact that this quantity phi, which is P1 plus P3, is identically 0 or not. I shall show that later on in the talk. But this is not something that you guess like that.
Yeah. So the size in epsilon has nothing to do with A, or
No, you fix A, and for epsilon small enough.
so epsilon depends on A in itself for the size?
Yeah, it might depend.
So does it mean A over epsilon square?
Sorry?
A over epsilon square, we can get the asymptotics of because epsilon depends in A.
No, but we shall, in this statement, yes, but we shall now get a T of epsilon, which is much better than what is here. And
For the first part, when A is approximating this, when it goes to this direction, will go to 0. Or?
yes, when the proof that I have given of this statement didn't say anything when you send A to T star. And what we want to do now is to say something. So let me give precisely the assumptions. So I define one over T star to be the supremum of some function, y gives gamma of y phi. I shall assume that this maximum is reached at a single point, y0, and that it is a strict maximum, and actually more precisely, that all derivatives of gamma phi at point y equals 0 vanish up to some order 2 kappa 0 minus 1. And I shall assume that at order 2 kappa 0, the derivative is strictly negative at point y0. So degeneracy assumption, which may be ensured, of course, choosing conveniently f0 and g0. Next, let me define the time t of epsilon. So I called e to the T star of epsilon square the blowing up time. Now let me take a time slightly smaller, that is, let me multiply at the denominator epsilon squared by 1 plus 2 delta prime, some positive constant. And let me take the inverse of that. So I get some exponentially small number. I multiply it by some power of epsilon for chemical reasons. And I get in that way an epsilon prime, which is exponentially small. And now I will take a time t of epsilon, which is close to e to the t star epsilon squared, in that sense that it is e to the t star epsilon squared times 1 minus epsilon prime plus or epsilon prime to the square. So that's a time which is more than the blowing up time, but pretty close to it. And the theorem will say that under these assumptions, at this time, pretty bad things happen to the solution. So let me state this. So I fix small numbers, theta and c. I fix some integer as 0, it will be the order of regularity. I take it long enough. And I'm finding then constants, epsilon 0 c, such that the following holds true. For any small epsilon, I may construct functions, what I will call perturbations, which enjoy the following properties. So as functions of x, these f and g are smooth. They are in hs0 plus 1 or hs0, and they are small. The norm is bounded by epsilon to the power r1 minus fixed small positive. And these fg also have decay properties. xf in h1, xg in l2 are also smaller than epsilon to the 1 minus. Then I shall solve our Klein-Gordon equation with Cubian linearity satisfying the assumptions that I said before. Taking as the initial data small perturbations of the f0, g0 that we were given at the beginning, adding to each of them f of x epsilon and g of x epsilon. So these are small perturbations because of the assumption. And the theorem says that if we solve the problem with these initial data, then we get a solution which is defined up to the time capital T of epsilon. And at time capital T of epsilon, something bad happens, namely inflation. Because
Jean-Marc, sorry, maybe it's a stupid question. If you take f and g equals 0 initially, then it is global.
yeah,
So
then it
you're
is global.
perturbing the global solution.
Yeah,
Okay.
because to have your t smaller than infinity, you cannot take it zero.
The P here is satisfied in our convention.
Sorry,
P is satisfied.
P satisfies no, P does not satisfy the condition. P satisfies I'm going back to the preceding slide of to the first line of this slide. So I assumed that this function y is phi of y has its maximum at some strictly positive number, 1 over t star. So in particular, this means that phi cannot be identically 0. And to say that phi is not identically 0 is to say that the null condition is not satisfied.
Then how you define this f0 and g0 are global solutions?
Yeah. Without the F and
Without this null condition.
Now,
In the next slide, you have f0 and g0.
Yeah.
yes, so f0 and g0 have been used to construct gamma. The function gamma of y depends on f0 and g0.
Yeah, but F0 and G0 will generate a global solution for the,
No,
no.
no.
It's just the initial data.
F0, G0 are initial data.
Okay.
They will generate some approximate solution that blows up, and our real solution will be close to this approximate solution corresponding to the data F0 and G0.
Okay.
What I say is that with this perturbed data, I get a solution which is defined up to time T of epsilon, not a global solution. And if I were taking, if you were removing the perturbations, the solution will not be global neither.
Well,
No.
so you can also take the red part be 0.
No, because well, as I shall explain later, I'm not able, to construct a solution, a true solution of the equation, which has the properties that shall state starting from F0, G0. What I say is that if I take F0, G0, satisfying the different assumptions that I have given, then I may construct some blowing up solution, or not a blowing up solution, but some solution with no inflation from initial data, from a convenient initial data, starting in a small neighborhood of F0, G0. This is, if you want, this is not a theorem which tells you that for the explicit, or for the initial data F0, G0, you have global, you have inflation of norms. It tells you that taking F0, G0, satisfying the assumptions, you may find in a neighborhood, in an arbitrary small neighborhood of F0, G0, initial data that will bring the norm inflations that I should describe now.
Okay. So can you make this epsilon and the G epsilon the size independent of the epsilon you put in front of F0 and G0? Can you make it different, for example?
Oh no, but I want to take it. I want F and G to be small perturbations of F0 and G0. So
So
the smaller these factors, the better.
Yeah, the smaller the better. I mean, if you can take it arbitrarily, for example, any delta from any delta, then or any epsilon independent of the previous epsilon, then it means that when you're sending delta to 0, then it will reach F0 and G0. Right? So for example,
Epsilon is, yeah, in fact,
this epsilon is a small epsilon, and
yes.
then you introduce another parameter, small parameter. For example, you replace this epsilon to the 1 minus theta by any delta, and the delta can be independent of a small.
Well, not really, because we shall see. We shall construct these perturbations F and G, solving an equation which contains already the epsilon.
Okay.
It will have remainders of size epsilon or power of epsilon.
Somehow.
So let me give a statement concerning non-inflation. So the statement says that at time T of epsilon, if you compute the value of u in infinity norm plus dtu in infinity norm, you get epsilon over the square root of T of epsilon, which is the dispersive decay you expect for the Klein-Gordon equation, but multiplied by some inflation factor, I of epsilon, which is bounded from below by T of epsilon power 1/2 minus a small constant. So T of epsilon is a time which is exponentially large. And so what we see is that this inflation factor almost cancels out what would decay given by dispersion. And so this is the property which contradicts the fact that unlike in the case when the null condition is satisfied, we have some dispersive decay of the solution. We spoil the dispersive decay if we take the solution at the time T of epsilon close enough to the road. And there is also a similar statement concerning the L2 norms of the solution. So this theorem gives a result of norm inflation. It does not give a blowing up result.
Do you believe it blows up or it's?
Well, let me
At the end.
let me explain why one gets only norm inflation and not blowing up. So the point is that the blowing up property is not expected to be stable under perturbations of the nonlinearity at the difference with blowing up. And let me explain this on a very simple toy model. Let me consider COD, y dot equals y cubed over 2. With initial condition y of 0 equals epsilon positive. So the solution y of t equals epsilon the square root of 1 minus t epsilon square blows up at time 1 over epsilon square. Now perturb the nonlinearity multiplying y cubed by 1 minus y square, so that for small data the perturbation is initially negligible. Take the same initial condition y of 0 equals epsilon, then it is easy to see that because of the sign I have chosen here, the solution will be global. Nevertheless, the solution remembers in some way that it comes from a blowing up solution of the unperturbed equation. Because if we compute the value of this global solution at some time t epsilon, which is epsilon to the minus 2 times 1 minus a small quantity, say a quantity behaving like epsilon to the delta for a positive delta, then the value of the solution at time t of epsilon is of size epsilon to the delta. So if we take delta small, it shows that at time t epsilon, the solution is much bigger than the solution of the initial condition. In other words, we have had inflation of the size of the solution, in spite of the fact that the solution is global. And so this shows that while blowing up was not perturbed, was not preserved the perturbation of the nonlinearity, a property like in non-inflation is preserved. And it turns out that, as I shall explain soon, the fact that we deal with a property which is stable under perturbations of the nonlinearity will play an important role in the proof.
Sorry, but in the previous theorem, if you have C equals 1/2, then you will still have that it's of size epsilon to the t to the minus 1/2, right?
Sorry?
C has to be small over there.
Small constant is talking about the small constant C.
C.
The
Okay.
I epsilon.
Yeah, but moreover, here you have here you are in one space dimension, so you have dispersion, and so what you have to compare is not the size of epsilon, but the quotient, if you want, between this and the dispersive decay. This one respect of T of epsilon does not happen in an ODE model because you have no dispersion in this case. Okay, so let me now start explaining the idea of the proof. And first of all, let me make a reference to some works of Cazenave and Martel, Cazenave-Martel-Jao, who have constructed blowing up solutions for the following equation. So the theorem concerns solutions in any space dimension with covenant linearity depending on the dimension, but I'm just singling out the case, the one-dimensional case. So you consider a Schrödinger equation, capital DT minus 1 over 2 capital D squared V equals alpha modulus of V squared, where capital D is, of course, 1 over I d over D, capital D is 1 over I d over dx. So if in the right-hand side alpha is real, then one is in the case of, one should understand the condition that alpha is real as a sort of null condition. And in this case, it is well known that you have the global solutions for small data. Now, in their papers, these authors consider the case when alpha is not real. And then, in this case, they constructed solutions that blow up, for instance, at time t equals 1, and that are global in the past. And so we shall use some of the arguments that work for this equation, but there is an extra difficulty which will appear, and which is related to the fact that in this equation star, the nonlinearity is invariant under multiplication by complex numbers of modulus 1.
So
Such a property.
I'm confused here because so are you going to use their result or
No.
no?
I'm
No?
not
So
going.
you are just comparing.
No, I'm not. What I say is that I shall use some of the ideas in their method of proof.
Okay. Whereas, like in your construction, the growth happened for both t going to plus approaching. I mean, for you, it will not be global from at minus infinity, right?
No.
Property of growth, you have it on both sides.
No,
In your case.
No, it depends on this, this function gamma of y phi of y.
Okay.
If I have only if it is positive with just a maximum, that will blow up
only on one side.
On one side, but it could as well blow up on both sides. So let me rewrite our Klein-Gordon equation as a first order equation. So the Klein-Gordon equation is a second order scalar equation. We may write it as a first order system, and introducing a complex valued unknown, we may write it equivalently also as a scalar equation, but with an unknown v, which is c valued. And so the equation is dt minus square root of 1 plus dx squared v equals some cubic nonlinearities.
Jean-Marc, I suggest you recall what is the meaning of dt.
I said already it's 1 over I over t. And so in the right-hand side, we have two types of terms. We have a term that I shall call characteristic or resonant, which is a cubic term, which is bilinear in V and linear in V bar. This is a term which has the same invariant property under multiplication by complex number modulus 1 as the right-hand side of equation star. And then on the other hand, we have also the blue terms, the non-characteristic ones, which are either trilinear in VVV or bilinear in V bar, linear in V, or trilinear in V bar. So these terms are usually, in the framework of small solution, not that annoying, because one may eliminate them by normal forms. which means one may modify V in order to get a new equation where only the red term remains in the right-hand side. But of course, when you do that, you generate some errors. That is, you generate quintic perturbations that appear in the right-hand side. And this is because we want to do that we need to limit ourselves to study a property that is stable under perturbation, since we want to be able to perturb the nonlinearity by higher order terms. And so, as I explained, non-inflation is a property which is stable by perturbation of the nonlinearity, while blowing up will not be. And that's why we study this question of non-inflation. So now, let me give the strategy. Well, the first step in the proof is to construct an approximate solution. So I call U up a function given by an ansatz, which has the following structure. First of all, on the first line, I get terms which are oscillatory because they are multiples of e to the I t phi of y, where phi of y is square root of 1 minus y squared, and y exceeds over t. So this t phi of y is just square root of t squared minus x squared, the phase of oscillation of linear solutions. So I multiply this oscillatory term by t to the minus L over 2 for L going from 1 to some integer n, by some convenient power of epsilon, and by a factor a L1 of s y epsilon. So S here denotes epsilon squared log t. This will be smaller than the time t stars that I introduced earlier. And these AL1s will satisfy upper bounds of the following form. So let me insist on what is the most important point. It is that we have an upper bound in terms of negative powers of a quantity which at point y equals y0 vanishes when s goes to t star. So if this upper bound is always also a lower bound, it means that this AL1 actually blows up when s goes to t star. So this is this property which will provoke the norm inflation.
And excuse me, can you explain a little bit about why the approximate solution looks like this?
Why
the approximation solution looks
well,
like
you know, if you take a linear solution, it behaves like t to the minus 1/2 e to the it phi of y.
yes.
Now, these factors will appear because of some equations that I shall get later, when I will plug this and that in the equation and get what I get, and see what I get for the coefficients. And then we have also other terms, the ones that I shall call non-characteristics, which are terms which have the same structure, except that we have e to the I q t phi of y with a q odd equal to 3. So such terms should appear because when we compute our cubic nonlinearity on U up, if we take the cube of quantities of that type, we shall get terms of that form with q equals 3, etc. And so these terms have the same structure as the preceding one up to this change in the phase. Let me remark also that since these quantities are allowed to blow up when S goes to T star, it might be that actually the successive terms in the approximate solution get bigger and bigger, which is not what we want for a solution constructed by successive approximations. We would like that when L increases, the terms get smaller and smaller. But each of these terms is multiplied by a power t to the minus (2), and t is very large. And so what we shall see that we shall optimize between the growth of this quantity with S replaced by some square of t, and the t to the minus (2). And this optimization will give, will impose that t stays smaller than some capital T of epsilon, which will be chosen in such a way that it is as close as possible to the blowing at the time, but not too close, in order that each term in this U hat is small, and actually when L increases is smaller and smaller. On the other hand, of course, we want to take T of epsilon close enough to the e to the T star of epsilon squared, so that the first term, the main contribution, will display this inflation norm that we are looking for. Now, let me explain.
So Jean-Marc, do you have a description of the Fourier side? You
No.
can write down
No. This is purely on
physical side.
physical side. And so let me explain, well, answer one of the previous questions, and let me explain actually where this AL1 comes from. Well, consider the first contribution, A11. So you plug your approximate solution in the equation, and you see what you get for A11, what kind of equation you get for A11, but the main order. And you get an ODE of the following form. You get an ODE saying that omega 0 of y, so omega 0 of y was from some function introduced earlier. It's not necessary to remember what it is, just a positive quantity. So omega 0 of y ds A11 is equal to a nonlinearity, modulus of A11 square A11, times a complex number, 1/2 of phi plus epsilon. And that's here that we see coming the null condition. Phi of y was the function that I introduced earlier, which was characterizing the null condition by the fact that the null condition is equivalent to phi identically zero. Psi is another function which may be written also explicitly. So when phi is identically zero, this complex number is purely imaginary, and it is easy to see that this equation has global solutions, and that these global solutions are bounded if you take a small initial value. On the other hand, if phi is not identically zero, then the solution of this equation goes up infinite time. And actually, under the assumptions that we made precedingly, that allow you also to identify what should be the right initial condition for this ODE, you may prove that your A11 is actually bounded from above by T star minus S power minus 1/2 when y equals y0. Y0 was a point where, the maximum of the expression which was giving 1/T star was reached. But what is important is what happens to y equals y0. And so this A11 is bounded from above by T star minus S to the minus 1/2 y0. And this upper bound is optimal, that is A11 of 0, does blow up at time like T star minus S to the minus 1/2.
So why, if you have a bound that goes up to the, does it mean that the function goes up?
No, I don't say, I say that this implies that so A10 is given explicitly in terms of data. So this implies that you have a bound of that type, and also that you have a lower bound of the same type.
Oh.
So because essentially you have an ODE that you solve quite explicitly, so you see that this is a bound which is optimal. So, and once you have constructed your A11, then the other coefficients that were appearing in the approximate solution may be constructed also solving successively convenient ODEs, which contain in their source terms, for instance, this A11. So this is this A11 that drives everything. So when you construct your coefficients in that way, you may check that finally your approximate solution, UR, is a good approximate solution, in the sense that if you define RR to be what you get making the difference between the operator acting on UR minus the nonlinearity computed at UR, you get that your RR has quite the same structure as UR itself, except that the sums start at some large index, L equals n plus 4, L equals n plus 2. And so because each of these terms is smaller and smaller when L increases, this R will be actually essentially as small as you want when you are at a time smaller than the T epsilon that I introduced before. So in that way, one has constructed an approximate solution. This approximate solution, because of the behavior of A11 that I explained, satisfies the inflational properties that we have introduced above. And so to conclude the proof, you need next to construct a true solution which will be close to the approximate solution. If you may do so with a close enough, with a small enough error, then you will be done. So let me explain how one does this last part of the proof. So I have written precedingly the equation as a scalar complex value equation. So say an equation of the form dt minus square root of 1 plus d square u plus equals cubic terms in u plus and u minus, where u minus stands for minus u bar. So from the approximate solution of second order Klein-Gordon equation, I may define a complex valued approximate solution of this star equation. I call it u plus r and u minus r for minus its conjugate. And now I study the error, namely the difference between the true solution and the approximate solution. So I call d plus the difference, and making the difference between the equation which is here and the equation satisfied by the approximate solution, I get that v plus solves dt minus square root of 1 plus d squared plus equals, well, three linear terms in v plus or minus, two linear terms which are linear in v plus or minus and linear in the approximate solution, three linear terms which are linear in V plus or minus and linear in the approximate solution. And there could be also, of course, some remainders that are linear explicitly coming from the fact that the approximate solution is only an approximate solution and not an exact. So this would be a source. And so what you want to do now, well, you want to solve this equation started at time t equals t of epsilon with an initial condition v plus equals 0. And you want to solve backwards and to show that your solution exists up to time t equals 0, and that at time t equals 0, it is conveniently small. Because in that way, you will have written your exact solution as the approximate solution plus something which is small at the initial time, which means that you will have modified the initial condition F0, G0 used to construct the approximate solution only by a small perturbation. And in addition, you will know that at the time t of epsilon, your exact solution u plus is exactly given by u plus up, and u plus up displays this inflational property, which was the conclusion of the theorem. So you will have got a true solution, which with non-inflation at time capital T of epsilon, and which at the initial time is close to the initial conditions that were fixed at the beginning. So let me say that in the right-hand side of this equation, you have again, on one hand, characteristic terms. That is terms like, which are pretty known, v plus, and v minus. These are terms modulus morally of the form modulus of v plus squared plus. And then you have also non-characteristic terms, which are terms like, for instance, v plus, v minus, minus. These non-characteristic terms are terms that you get rid of by normal forms, as I said already. And so, performing such normal forms, you may rewrite your equation in terms of a new unknown that I call W plus, which satisfies an equation which has exactly the same form as before. dt minus square root of 1 plus d squared W plus equals different linear terms plus the remainder. The linear terms being now all characteristic ones. By this, I mean that the indices I1, I2, and 3 satisfy I1 plus I2 plus 3 equals 1. And the remainder contains some quintic perturbations, and it contains also the error coming from the fact that the approximate solution is approximate and not an exact solution. And so, to explain what you do finally in order to solve the equation, because you want now to solve such an equation with an initial data which is 0 at time t of epsilon and up to time t equals 0, or down to time t equals 0. And so, as a model, let me consider the case when these complicated regional terms will be given just, for instance, by modulus of W plus square W plus modulus of W plus up square W plus the source term. And so the key point is the fact that if you have constructed your approximate solution in an accurate enough way, your source term will be very good. Actually, it comes from the error when you plug your approximate solution in your equation. And because of that, you may arrange so that your source term decays like t to the minus 2, for instance. And moreover, when the time t goes to the blowing up time into the t star epsilon square, this term vanishes like a large power of that small quantity.
Zero is the order of the expansion. No?
No, well, and 0 is related to the order of its expansion, but you fix it large enough. And similar statement holds true if you make act on your operator, on your R, the operator L plus equals x plus t dx over Japanese bracket of dx, which is an operator which is constantly used in this framework in order to capture the dispersive properties of the equation. And so I guess that because my time is essentially over, I shall not explain much the rest of the proof. I shall just say that you have to make a bootstrap argument in order to prove for your solutions a priori estimate a Sobolev one, an L2 one for the action of L plus and W plus, and a dispersive decay saying that your W plus decays like one of the square root of t. So to prove such a bootstrap, you assume that such properties hold true on some interval, capital T of epsilon. Remember that you started from the time capital T of epsilon and want to move backwards. You assume that these equations, these inequalities are satisfied with constants A0, A1, B on such an interval. And using the equation, you prove that actually they hold true on the same interval, but replacing the constants by half of them. And so then, because of, when you have done that, then you may push your capital T down up to T equals. And so I won't read what is written on this last slide. I will just explain why it is important to have constructed your approximate solution in a precise enough way. So you know you make energy inequalities. And when you make energy inequalities, you have an expression like an integral of the infinity of the approximate solution to the square times the quantity you want to control, here L plus W. So in other words, you will make some groundwork argument to deduce from such an estimate a bound for L plus W. And the difficulty comes from the fact that this approximate solution has bad behavior close to the blowing up time, because by the construction that I showed earlier, you may see that this term behaves like 2 to the minus 1 times a quantity t star minus epsilon square log 2 to the minus 1, which goes to infinity when tau goes to t to the t star epsilon square. So when you do a groundwork argument with such a quantity, you have to make appear the exponential of the integral of such a quantity, which gives you a large term, a large power of a quantity which is loaded up. And the reason why you may cope with this large power comes from the fact that you have constructed your approximate solution such that the remainder in the equation applied to the approximate solution behaves nicely, namely with a large factor of a large power of t star minus epsilon square log 2, where n0 may be taken as large as you want, taking enough terms in your approximate expansion. So this factor will cancel out the bad term here, and this is because of that, and you may close your argument
Your
in your bootstrap.
size of the node, does it saturate, or you can make it as small as you want as long as you push? Oh,
No, you can push things as long as you want. Okay, and so this concludes my talk. And so to finish, let me say, thank you, shukran for your attention.
Oh, thank you. Okay, are there questions?
I'm not familiar with the field before, but so in the non-linearity you took to be a homogeneous polynomial of degree 3.
Yes.
So in the counter example, is it not a homogeneous polynomial? So when it blows up?
No, it's the counterexample of unknown. They are explicit expressions like ux square ut. You know? So cubic expressions.
So it seems that you use the null condition, or actually the invalidity of the null condition, to say that the A11 blows up.
Exactly.
Right?
This is what gives. This is essentially equivalent.
This is
to
where you actually use that.
Yes, exactly.
So basically, can you get another condition similar to this null condition from A12 that blows up, or?
No. If if A11 blows up, then you get what I explained. If A11 does not blow up, this is when the null condition is satisfied, and then you have global existence. You know, the other terms, when if you use null condition is satisfied, the other terms in the expansion will be smaller than the first one. So it's they want to spoil.
Okay, are there other questions?
Does the similar phenomenon appear in other descriptive equations such as
Well, in Schrödinger, I gave references to work of Martel and different co-authors.
what about wave equation?
What about wave equation? I know. No, you speak of wave equation or water wave equation. So in the case of wave equations, the point is that then essentially everything is known, and the situation is quite different regarding to the way singularities fall. Here, the singularities come from singularities of the node, that I have explained. This is related to the fact that the linear behavior solution is an oscillatory behavior for Klein-Gordon. If you take the wave equation, then blowing up is known in this framework of small initial data. Blowing up may appear in this case in 2 or in 3 space dimension and not in higher space dimension. And the phenomenon of blowing up is different. And this is a phenomenon related to a Burger's equation. And this is because the structure, the asymptotic structure of linear solutions is then completely different. It's more a conormal structure along the wave cone than an oscillatory behavior. In particular, here, when things blowing up happens in a point which is inside the wave cone, while for wave equations, blowing up always happens at a point at the wave cone.
So for this model, as you said in this OD, if you add some higher order polynomial, then this cubic the cubic equation become a cubic plus order of 5, then you have a global solution. So how about this one? If you change this homogeneous order 3 polynomial by adding some 5th order, can you make it become global in this?
No, that's that's well, that's a question of real blowing up, not of nomenclature.
Yeah. Okay. Yeah.
I mean, and that I don't know at this point. Well, there are examples of blowing up solutions, but when these examples are quite similar to us. one does not construct when you're not able to give the asymptotic behavior at low level of these solutions. One starts from a solution, constructs from it some integral quantity, and shows that this integral quantity satisfies the ODEs at closure. So you know that your solution of your PDF closer, but you do not know how to close it.
And for developing a nonlinear Klein-Gordon equation with cubic nonlinearity, we know there exist global solutions, but also modified schedule.
Yes.
For the decay, we have a log fraction for the linear decay.
Yes.
I want to ask you if this can be seen as the infinite time version of the normal inflation.
No, well, no, the actually modified scattering happens already in the case when the null condition is satisfied. It happens, and what happens is that when the null condition is satisfied, your global solutions do not behave exactly as linear solutions. Their oscillatory behavior is e to the I square root of t squared minus x squared plus log t times some quantity. This is the modification of the scattering. When the null condition is not satisfied, you don't really see that because this modified scattering happens at times which are larger than e to the c over epsilon square. To see it, you have to have epsilon square log t goes to infinity. And here, when you are in this case, epsilon square log t stays smaller than the constant, so you do not really see that. But you do see that in when the condition is satisfied.
Okay, another question?
Just one question. So can you say more and try to estimate to say that the inflation can start for a long time before this T epsilon or what? Because your inflation is at T epsilon, but I guess it can start a large time before this T epsilon, no? Because the quantity that you get, it goes past to infinity.
Yes, so well actually no, you get you as I said, everything comes from the expression in the approximate solution. So you see the first term of the approximate solution, you know it essentially explicitly.
So it get better than this T epsilon for the inflation, or
no, not no. I mean, for T smaller than T epsilon, you will get that essentially the same rate of inflation. You will get T. I wrote, epsilon square over square root of T epsilon times T epsilon to some power. But this is true, of course, for T smaller than T epsilon. I mean, you will have epsilon over square root of T times T to the same power for T smaller than.
Yeah, but something logarithmic, for example.
You mean to improve on the exponents? No, that well, that I don't know, and I'm afraid it will be quite technical.
Okay, any other questions? Thank you.